Good morning. Can you hear me? Good. Yes. See the in-person schedule. It just get updated. AP 108. All right. So we will have more announcements, but the in-person schedule came in, and from what I understand, I mean, we'll post announcement with. I think it will be on the first week of February that we are gonna be in person again. If you have some problems with, I don't know, being in a different country or whatnot, you should contact us. Okay, so if there's some problem uh, with not being able to attend, um, please contact me and Camelia together. Okay. Right. I will try to have some online parts. I was thinking to have a Zoom session during class so that everybody can get help. But we'll see. I mean, we can talk about this. All right. Any questions? Administrative or anything? Okay. Fine. So, all right. Yeah. So last time we talked about matrices, and that matrices are an example of a vector space. Okay, this is where we left off. Now let's talk about another example, namely a space of polynomials. So these are an element in Pn of f is of the form a0, a1, x, all the way to an, xn, and our coefficients are in the field, and x is fixed. So we're not allowed to put any number to x. It's just some variable, and the calculus is done over the coefficients. So a0 plus a1x plus b0 is equal to a0 plus b0. Okay, so any calculus that you do is done over the coefficients. Okay, all right. Okay. By the way, can I get some quick? Yes. Yeah, I will talk about it in a second. But can I get a quick survey? Do you prefer in person or online? I mean, we will do in person. I just want to see like roughly. So if you can, yeah, that's what I thought. So it's a mix. Yeah, okay. I will try to have both. Yeah, I will try to do in person and then, right. Yeah, I will try to have both. All right, good. Good to know. All right, yeah, so I wasn't sure because it's so early in the morning and I wanted to make sure that what you guys feel like. But I mean, we're gonna do in person regardless. Like it's not it's not up to us anyhow. All right, so yeah, Pn of f. Pn of f are all the polynomials of this form. These are the this is the space. So you're allowed to vary the polynomials, and x is fixed. So you might as well call it Pn of fx, because in a sense, x is a fixed variable. Is that okay, Kellyanne? As in the type? Oh yeah, x will be, I mean, we're sort of trying to leave it abstract, but yeah, x will be, x is fixed in the field as well. Yeah, but in a way, we try to suppress it, to not think about it. Yeah, because all the calculus is done over the coefficients, but we're not really touching x. Yeah, okay. All right, let's see, closed under addition. So yeah, so you give me two polynomials in Pn of f, x, let me do it like that way, even though we should call it Pn of f, but I want to make sure that we understand that x is fixed. So you're given two polynomials, you have their expansion, so summation of pi x, pk xk, and q is qk xk. And oh, I see, I made them go a little bit higher. Yeah, so one goes into Pn, the other guy goes to Pn plus 1. And right, I think I'm over confusing this. Let me just say that both of them are in N. I think this is, it's unnecessary. I don't have to confuse you. So let's just talk about like this. So yeah, so we have two guys in the same polynomial space up to N. And yeah, you simply add the coefficients like that. And then you use that the field is closed under scalar under multiplication and addition. Okay, so this is one of the axioms, closure of the field. Therefore, you get another polynomial h of x whose coefficients, call them, I don't know, h0, h1, hn, they're all in the field. So this guy is in Pn of f. Is that okay? If we define PNF to be a vector space, then can we do things such as diagonalization on the vectors within this vector space? So the answer is yes, but I have to understand what you mean by, because there's no matrix here, right? So a better word to use is, yeah, there's no vector space here. So, but we will come back to this. So there's a thing called spectral theorem, and you can still do these things, but there's no matrix here. So it's kind of tough to say diagonal, but we will come back to this. There is a notion of decomposing operators into eigenvectors. Okay, we'll come back to this. This is a little bit too early for this. All right, so another one of the axioms was to show that there's an additive identity, and a natural choice is what? You take 0f, the identity in f, and you make this be all the coefficients. So namely, you set ai to be 0f for I 0 to n. Okay, so this is our polynomial. This is a polynomial. This is the zero polynomial. Okay, this is the zero polynomial. And the question is, okay, does it act as a additive element? Well, then, yeah, we have our generic polynomial p. We add their coefficients. Oh yeah, I should have, I don't know what happened here. So I will fix this typo. and then this is Pn of 0f. So you add the 0 at each coefficient, and then you use that Pi plus 0f is equal to Pi, because this is true in the field. So again, we know that something works out for the fields, and then we push it forward for the vector spaces. That's the trick. So whenever you see things like this, always try to go back to the field. Okay. Is there something? Yeah, there is, and we're gonna talk about this. Yeah, like I said, there's a thing like spectral theorem that works for vector spaces, and there's no need to, there's no matrices there, but there's other things called operators. So we'll come back to this. It's a bit early for that. All right, and then what else? And you can also define an additive inverse. That was one of the axioms. So you give me some generic polynomial. Then if you want to define its additive inverse, you take the polynomial whose each of the coefficients are the additive inverse in the field, right? So remember, in a field, every x has minus x in f, so that x minus x is the 0 element of the field. So this is what we took. We took this minus pi's to be the additive inverses of pi. Okay, and then once we do the additive addition, the coefficient addition, we're just left with the 0 polynomial. Okay, so that's the yeah, you're left with the 0 polynomial. Okay, all right, good. Live transcription be enabled. Enable, sure. Okay. All right, is that okay? All right, let's go to the other example. So this is the space of functions, namely, so func of f are all the functions from the field to the field. And the most standard example are real numbers. So we take all the functions from the reals to the reals. We could have taken from complex to complex. I mean, I cannot really visualize it, but let's pretend it's something like this, even though it's not really. It's 4-dimensional, so we cannot really visualize it. Okay, so this was the space. So namely, you now take functions. You know, we took polynomials and we add them coefficient by coefficient. Now we add entire functions together. So let's do some calculus to see how this works. Okay. So let's see the closure. All right. So it's sort of the same idea with the polynomials. You fix your x. So x is a fixed unknown. Okay. You fix your variable, and then you try to do calculus with your functions. So the question is whether this element, this addition of two functions times a scalar multiple from the field, whether this is indeed in the field. And then what do you need to show? We need to show that h goes from f to f. That's what we need to show. That will prove that h is in this vector space of functions from f to f, right? That's the thing. So how do you do this? You look at the image. So you do your addition. So it's clear that h is evaluated at f because each of the elements are in F. But what about the image? Well, the image is exactly this. So we know that H goes from F into S. And these are all the elements, C1 f of x plus g of x, x in the field. But we know that for each fixed x, this is in the field because of the closure, because of F's closure. Okay, so that means that this whole set, this is a set, right? We're indexing over the field, is a subset of the field, right? Because each of these elements is in the field, okay? So then when you take their union, right? Another way to say it, this is the union over all x in F of elements in F. Then this union of things will also be in the field, okay? That's the trick. So then indeed, we get that H is a function from F to F. Is that okay? Is it tricky? So you can let me know. I should ask you some questions as well. I talk too much. So, okay, let's see. What's another one? Yeah, we also need the axiom of additive identity. And yeah, so here we have to make a decision, and the decision we make is we take f of 0 to be from F to the 0 element in F. Okay, this is still a function from F to F, namely it's the constant function. Like if we were in the reals, it would be this function over here, right? So it sends everything to the 0 element. F is equivalently 0. So it maps everything to 0. Okay. So this is our additive element. And then we do the same trick. We're trying to ask whether when you add them, you get back the original function, and everything you do it pointwise, meaning for each x, you need to tell me what happens to the functions. So for each x, we know that this is always equal to 0. So then we use that for the field, that since g of x is in F and 0f is in F, we know that gx plus 0f is equal to g of x because of the field, because we know that 0f is an additive element. In F, right? That's the idea. Okay, great. All right, what else? And yeah, I mean, I should leave something for you. So this is the additive inverse, and again, we go to pointwise because we need to come back to the field. If you fix X, this is just an element of the field. All right. If you have questions, just let me know. We can talk about it more. All right. So I added some non-examples. Let's go through some of them. So these are examples of not vector spaces. This is also in your homework. So I thought I should add some examples. Okay. So right. So I say that this vector space over here, which is just the so x plus y is equal to 1. So it's something like this. So when x is, what is it? When x is 0, y is 1. So it's like this. All right. Can someone give me an example that shows that this is not closed under addition? 0, 0 isn't in. Yeah, that's, but what about, let's do that is not closed under addition. What's a simple example? What do you think? Oh. 0, 1, and 1, 0. Right. So we have 0, 1 plus 1, 0 is equal to 1, 1. These guys are in W, but when you add them, 1 plus 1 is 2, which is not 1. Good. Simple. But this guy is indeed a vector space, and we will, once we go into subspaces, I will explain how to get this. So we don't have to go through all the axioms every single time. All right, another nice example, non-example, is you can break the commutativity of the addition. So you take functions f r to r, but instead of the usual addition, f of x plus g of x, you define this new addition to be the composition. Okay, so you take pointwise composition. Okay, so like for example, let's see, e of x with let's see, x squared. Okay, we define this to be e of x squared. That's the addition in this space. It has some nice properties. That's why I'm studying it. It has shown up. People who are interested in this kind of space, and it goes by other names, but it's not a vector space. So it doesn't have that structure. It has other structures. And the thing that fails here is commutativity. So if you add them this way, you get this result. So for x squared and x plus 1. And if you add them in a different order, you get a different result that's not equal to the previous one. So commutativity fails. So AB is not equal to BA. Okay. Is that okay? 2x and x plus 1. Yeah, because you will get something like 2x plus 2, and the other way you will get 2x plus 1. Yeah, great. Was that a type of, yes, that's a type of addition. So we like we get to define our addition, and we say, okay, take this space of functions, and instead of the usual addition that it's like normal, like e to the x plus x is as e to the x plus x. So instead of doing this, we define it as composition. Let me put square here. Okay. Is this the new vector space that we define? Oh, it's a counterexample because, where is it? So this is a counterexample because each one of them is in the space, right? 1 plus 0 is 1, 0 plus 1 is 1. And, but when you add them, like vector addition, right? So you have 1 plus 0 plus 1 and 1 plus 0, you get the element 1, 1, right? But when you add them, you don't get 1, you get 2. So W is not closed under addition. Is that okay? Oh, yeah, okay, good. All right, so yeah, we're here. Yeah, okay, so this is the this is an example, a non-example for commutativity. So you can have an interesting space, the space of compositions, but it fails to be a vector space. Okay, all right. If you have a question, you can tell me. Yeah, it has an associativity, it has an additive element, it has a lot of interesting structure, but not vector space. All right, what else? Yeah, I don't know. I mean, you can scroll through these examples. I have a bunch. Was there any interesting one? I think I want to talk about additive inverse. What else? Yeah, I mean, this is an example in your book as well. So let me make sure you understand it. So you take the positive quadrant and it looks like a vector space, right? You have a nice plane, but it doesn't contain negative elements. So you have that 1, 1 is over here. But if you want to have its additive inverse, which is one of the axioms, you will have to go down here, minus 1, 1 over here. But this is not in the space. So it's not, it doesn't contain its additive inverses, so it's not a vector space. Okay. Yeah, I think this is simple things. All right. Okay, time to do some proofs. First proof of our course. So this is in your textbook and we're gonna go over this proof. So, so this is one of the properties. This is not an axiom, this is a property. So the axiom was that 0v exists, but who says that? But maybe there's two of them, but maybe there are two. 0v and 0 prime v, right? A priori, the axiom doesn't say uniquely exists. It just says there is at least one, but this is annoying. So we have to make sure that at least there's one unique element. So it's just too confusing. And it turns out that there is. So if you put all the axioms together, we will show that there is one, only one. So yeah, suppose there's 2 0 elements, right? So x plus this 0, this v1 is x, and also x plus v2 is also x. So they both act as additive elements. Yes, Angela, we will to prove. So the question is, the textbook has a theorem labeled 128, and it says that, yeah, this is if W is a subset of V, you don't have to check all the axioms, you just have to check closure. And yeah, this theorem, we will prove it and you can use it, of course, yeah. I'm not sure what the question is. Does it suffice to only use? Yeah, you can use it. Yeah. Yeah, that's the whole point of the exercise. You don't have to test the axioms. I mean, I don't know ever. I will have to see the question, but yeah, okay, good. But yeah, I mean, please use it. It saves time. All right, so V1, V2 are additive elements. So they both equal to X. Okay. Oops. So what do we do? So you take X to be V1 and you take X to also be V2, right? So here's the trick. You have V1 is equal to what? V1 plus X. This is the X. And then V2 plus X, which is V2. So going from here to here, or if you like backwards, going from here to here, we use that V2 is an additive element. Let me erase all the stuff over here. So going from here to here, we use that V2 is additive element, right? When you add V2, you get V1. Going from here to here, we use that V1 is additive element. And going from here to here, we use commutativity. Is that okay? These are the 3 steps. Can we use proof by contradiction for this? Well, you can write it in the chat and I can check. Yeah. Okay, so hopefully you understood this. So we had to use commutativity in the middle step. Okay, that was the trick. All right, anyhow. Okay, what else? Yeah, another nice property is that when you multiply, there's too many notations here. This should be just, oh no, I know what I'm writing. So this is 0f times, this is the dot product of v, right? We equipped our space with the scalar multiplication specific to v. And yeah, so we equipped it with this, and we have that it's equal to the 0 element. A priori, this is not an axiom. So the only axiom we had is that 0v plus x is x. That was basically it. We didn't have this information that if you multiply by the 0 element of, I should call it additive element, because it's not always 0. So if you multiply by the additive element, you get the additive element of f, of v. So if you just multiply by additive element of f, you get the one of v. So this is not an axiom, this is a result. I see some questions here. Can we go about proving this? Yeah, I will. Okay, let's see. Can we go about proving this by saying x is x, since they're both? No, you will have to. Oh yeah, this is another proof, right? So can we go about proving this by saying x is x and then using the additive inverse? Yeah, that's another way. That's right. And x belongs to f. X belongs to f. No. X belongs to the vector space. So we're talking about the vector space here. Is that okay? Yeah. Yeah. This is where we're doing results for the vector space. So we're saying that otherwise it's obvious, right? For the field, 0f times x is equal to 0f. If let me call this y or something, not to confuse you. So when y is in f, yeah, okay, anyhow. Actually, is that true? Well, let me not say things that, because this is not one of the axioms. I will have to check. I think it is true. You can prove it. Yeah. Yes. Okay. Anyhow. But yeah, we're talking about the vector space. All right. Let's prove this. How do you prove it? Oh, and Rudrash had a question. I missed it. Like if we assume them to be two distinctive elements, if we, yeah, it's the same idea. We do the additive inverse. Yeah, that also works. All right. Okay, so let's prove this. If you multiply by the 0 scalar of the field, you get the 0 element of the vector space. So what's the trick? Here we use first the additive structure of the 0 element of the field. Okay, so going from here to here, we use star. So we added 2 times. From here to here, we use distributivity. Okay, and now we get the same element in both sides, right? We have called this A, and we got A plus A. And now what's the natural thing to do? You add the additive inverse. So So by adding the inverse of this A, so this is minus A, we get the following. So we have that A, oh, from here, yeah, let me do it from here. So we have A is equal to A plus A, and then you add the additive inverse to both sides. So this is 0V equal to A plus 0V. So you get 0V equal to A. Okay, I like this proof better. I don't like the other one. So you start from this, you add the additive inverse to both sides, and then you use that A minus A is equal to the 0 element of the vector space. Okay, that's the trick. All right. Okay. All right. So that was the. If you have a question, just let me know. So, okay. So now we can do. It's a little bit easier to work with the scalars. All right. Here's another element. Again, the axiom was that there exists additive inverse. It didn't say that that is unique, but not necessarily unique. Okay, so we have existence, but we might not have. This means exists, but not necessarily unique. Sorry, I'm confused as to why Cauchy's proof isn't. No, I didn't say. Did I say it's not enough? No, I said it's enough. Yeah, that's another way. Oh, yeah. Yeah, sure. Yeah, we could. Yeah, it's definitely enough. No, it's perfect. Yeah. Okay, so now we want to show uniqueness of the additive inverse. So assume that there's two of them. So they both satisfy the additive inverse property, namely that xv1 is the 0 element and x plus v2 cancels out with x and gives you the 0 element too. And I think, yeah, here I do this Cauchy's proof. So I add the additive inverse. So we start with v1 and here I use a bunch of stuff. So here I use that v1 x minus x is equal to, yeah, okay. Anyway, so here I do the following. I use that v1 is equal to v1 plus the 0 element, which is equal to x minus x. And then I use that v1x together give me the 0 element. Okay, so here I use additive inverse of x, and it doesn't have to be unique. I just need one of the additive inverses of x, and right, and then I use the same. I do the same way with v2, and yeah, so you have it like this. Is that okay? Will says, when you subtract x from both sides, you're doing x minus x. Should that equal v1 or v2? Then that's why. Right, yeah, this could equal v1 or v2, but it doesn't. So this proof is sort of similar to the one we did for the 0 element. In a way, we get a relation of a is equal to a plus a. Yeah, so exactly, x could equal either the minus x could equal either one, could be v1 or v2. It works either way. So I didn't want to write down minus V1 all over the place. I think it would be a little bit confusing. So I just use that there exists an additive inverse, and I call it minus X, and I work with that. It could be either V1 or V2. Is that okay, Bill? Yeah, it could either be either one. I just know
I was
there
saying
exists.
that in response to someone else in the chat talking about
Oh, I'm sorry.
two
Okay.
earlier proofs about the zero vector is unique.
I see. Okay, thank you. Oh, for Christian's proof, right? When we say V or plus V, what exactly does that mean? Is it a dot product and addition adapted to what? No, we're not talking about dimension here. I'm not sure where dimension came in. We're just talking about that this plus is specific to the vector space. So remember, right, for the functions, we had this function space W, and we defined addition to be composition, right? We defined it. It's our definition. So you can define your own way. You can have maybe this guy to be the, I don't know, maybe the power, something crazy like that. So, but then the question is, why even do crazy stuff like that? Because some of the spaces are interesting. So this composition space had some interesting properties. Is that okay, Kelly? So we get to define it. Okay, so we have uniqueness of the additive inverse, and then the final thing they state is this thing where you basically says that the additive inverse of this element is minus C times X. So it's just logical things that you expect from real numbers and complex, and but now you work with arbitrary fields, you know, like modular numbers, and you want to make sure that everything works out, right? So let's see how this works. So again, we start with where do we start? We start with this, and we want to show that this is the additive inverse. We want to show that this is the additive inverse of CX, right? So we add them, and we want to see that we get the zero element. From here to here, we use distributivity in reverse, okay? And from here to here, we use that minus C is the additive inverse of C in the field. Okay, so we go back to the field. And finally, we used our little result that 0 of f times x is equal to the 0 element. Okay, so we came back to using our previous result. Is that okay? Yeah, but how will it be rigorous in a proof if you can? I mean, as long as you're consistent, right? So some spaces are not interesting, some spaces are interesting. You know, vector spaces are a very flexible machinery, and many spaces are not vector spaces. So like the one I just mentioned is not the vector space, right? Like it's not. So we're not, like, all these things are results for vector spaces. They're not for that composition space. But yeah, but there's a lot of flexibility. I mean, because the world is complicated. I don't know, like people are interested on all kinds of objects. Yeah. All right. Now let's start talking about a little bit about subspaces, and we will continue that. We'll finish it up on Friday. All right. So like Angela mentioned, there's a very nice criterion for checking that a subset of a vector space is also a vector space itself. So, the standard example is you take W to be like X, Y, and then 0 in like R3. And this is inside R3, and it's and it looks like this. So this is the plane, right? Now, of course, this is not R2, so this is not R2, but it's very closely related to it, meaning that we have the same structure. The first two components are one-to-one correspondence with elements of R2. And so this is a typical example of a subspace. Okay. But it can be very annoying to show that this guy is a vector space. You will have to check each of the axioms. So here's a quick way to do that without having to go through all 7 axioms or 8, whatever they are. Okay. Can we say R2 is a, so no, we cannot say that because R2 has only 2 components. So I think I said that, but I have to be very clear about this. So these are like this, right? But this has no third component. So we have to be precise with this. So when you draw these pictures just mean that we have a 0 component. Is that okay? Parth?
Hi, sorry for speaking right now, but like, yeah, since I think we're done on the same thing, I remember like there was one example stating
Yeah,
that.
Parth, can we talk about this at the end?
Oh, sure, absolutely, yeah.
Okay, thank you. Yes. Because I only have like a few minutes, so I want to state the criterion at least, and then so, but okay, like Angela said, this criterion is very interesting because you don't have to go through the axioms. So if you start, here's another way to think about it. Suppose you're given some space and you want to know, is W a vector space? Okay, so you want to know, like, is this a vector space? Well, here's a trick. Step 1, find some V, some VSV where it's easy to know or it's known from class results. Find some V, so find some W inside V. Let me say find some V. Find some V known to be VS from class, okay? Then you can just use the criterion that we're gonna mention. So this is a cool way to show that something is a vector space. All right, I might as well just mention this criterion. So you just have to check closure, okay? So let's go back to our example. So X, Y, 0 in R3. Let's check that this is a subspace in R3. Okay, let's do that here. So you just have to show closure. So you give me 2 elements, A, B, 0 and C, D, 0, and then let's multiply by a scalar. All this stuff are done coordinate wise. So we have lambda A, lambda B, lambda 0 plus 0, but this is just lambda A plus C, lambda B plus D, 0. And this is, each one of them is a real number. So the whole thing is a in R3, but it's also in W because the third component is 0. Okay, so W is closed under addition and scalar multiplication. Okay, so W is a vector space. Okay, All right, so at least I introduced the criterion, and tomorrow we will, on Friday, I mean, we will continue proving it and yeah, do some examples. All right, thank you. I'll stick around for questions. Make sure to check the timetable. They just posted it last night. Yeah,
Like,
perfect. Yes.
sure. Sorry for intervening in between before. I'm so sorry about
No,
that.
it's fine. Yeah, go ahead. Tell me.
So like for this thing, right? I think it was on one of the slides. I think it was slide number 5 on this
No,
presentation.
but I
Yeah.
was just trying to, I think I fixed it on the, so
Okay.
I added the detail that I only mean this as zero padding, like meaning,
Okay.
so
So we essentially like add extra zeros.
yeah, you just have to add the zeros. Otherwise, it makes no sense, of course.
So we can't strictly say that it's like a proper subset, like R2, for example, is a
No,
strict
because
subset.
I mean, you cannot embed it. It's not, I mean, it's not, it like you have, 1, 1 has nothing to do with 1, 1, 0. I mean, of course it has, but just formally, like very like, they're not related.
That
Only
makes
when you
sense.
add it, then you can start talking about it. Like,
And
for example, you cannot add these two guys, right?
exactly, yeah.
So, I mean, that makes no sense.
That makes no sense. That makes sense. And so likewise goes for Rn and Cn, right? So when we say that Rn is kind of like a subset,
Yeah, only by zero padding. Yes.
by zero padding.
Yeah.
All right. So it would be sufficient to just like, so in like writing summary, just be like Rn is, for example, a subset of Cn, and in a bracket you write with zero padding.
Yeah, I mean, I will, to be even more, I mean, because now we're talking about tests and stuff, I will actually just use the notation I used, meaning W is something like this. And you add the 0 elements. Yeah.
That makes sense. So that was one of the questions that popped up. I actually had so I had questions regarding the our first written homework, right? So the first one is like the last question's last part essentially asks us to write a
Oh wait,
conjecture,
Angela
right?
has a question about this. Let's
Sure. Yeah.
sorry, so XY0 is not equal to R2, right? Can you explain exactly why again? Is it because AB0 transpose is not equal to, yeah, exactly. That's exactly right. So yeah, they're not the same element because it does not have a third component. So you cannot do calculus with it. You cannot like add them, right? Like this doesn't mean you cannot add two vectors of different size. Yeah, exactly. XY0 is a plane in 3 dimensions. So you have to zero pad. Okay. Yes. Okay. Yeah, go ahead for homework. What did you want to say?
Like, so like, our written homework, right? So like, I think the last question's last part essentially asks us to write a conjecture. So I was wondering, how do you expect us to write a conjecture?
Do you know what? I asked this exact question to the coordinator.
Oh, wow.
And
Okay.
it's funny that I knew it's going to be a problem. But I don't know. From what I understand, it's very like loose.
It's very loose. Okay.
Yeah, it's very loose. I wouldn't worry too much about it.
So
just
for example,
make sure you write down what the number is. And then I will personally just give like an explanation of why I think this is a good number. But it's supposed to be like a very loose question.
So like the basic framework can be something like you write a sentence that you think this is the answer, and here is some supporting information.
Yeah, exactly. Yeah, exactly. It's not meant to be like
rigorous, like proof kind of thing.
No, it's not rigorous, no.
And finally, so like in one of the questions, I think I'm gonna be using the modulo thing that we learned, like in the square brackets M and P. So okay, can I annotate? Because there's one specific thing that I intend to use to prove distributivity. So in that sense, it's like x plus y in the square brackets 3 plus z in a square brackets 3 is same as x plus y plus z in a square brackets 3.
So what's the question? Like, are you
So
asking?
can I use this directly?
Well,
or
yeah,
like,
can you, because it's hard to do math over. Can you put it on Piazza and then we can talk about it?
oh, sure, absolutely. Yeah, I
Yeah.
should have done that. Yeah. Mhm.
Yeah,
Yeah, perfect. That these were my questions. Thank you so much. Yeah.
okay, good. Okay, any question? Anybody?
Hi, Professor.
Yes. Who is
Can you,
this?
Hui,
Oh, Hui, okay, yep,
can you go to slide number 12?
sure. Yeah, I'm here.
Yeah, so the last line, it says zero element of field times x minus zero element of f times x equals to zero element of vector. Like, I don't understand why it equals to the zero element of vector.
We were proving this. This is the, I also use better notation. So this is the claim, and then we are proving it.
Yeah.
And then we start, and then we start from here, and then we do this trick where we split it. I mean,
Mhm.
this is the proof of this thing that you just said.
Yeah, like in the very last line.
Yep.
Yeah, like why it equals to zero element of vector.
Oh, why is it? Oh, because why is it the zero? So we use this relation, right? From here, we
Yeah.
proved that 0fx is equal to 0fx plus 0fx, right?
Yeah.
Now subtract 0fx from both sides. So 0fx minus 0fx equal to 0fx plus 0fx minus 0fx, right?
Yeah.
This guy here is the zero vector space element, right?
Why it equals to the zero element of vector space.
No, it's because they're inverses of each other. Like, you know what? I might as well use different notation just to. So we prove that A is equal to A plus A, right?
Yeah.
Then add minus A. So minus A is equal to A plus A minus A, right?
Yeah. Yeah.
This guy here is 0V, right?
Yeah. Right.
And then this guy over here, you group these two guys. So it's 0V.
Okay. Okay.
So is that okay?
Yeah. Yeah. Okay.
Yeah, that's a good question. Yeah, it's very tricky.
Okay. Thank you.
Yeah, you're welcome. Oh, Kellen, Prof, what did you mean by checking the timetable? Oh, there's a, I mean the Arts and Science. They posted the location. I just saw it. It's the KP building, the new engineering building. Yeah. Arshia, can you explain the functions of F quickly? What are the function elements and what's the underlying field? Yeah, let's go to the example. Which slide was it? Oops, over here. I think this guy. Right. Here we have everything. Yeah, no, I wish more people ask questions. This was a tricky one. So yeah, we take this, let's do the real numbers. So these are all the functions from real to real. So they all look like this. And the way we define addition and multiplication is pointwise. So you, for each x, you can add them and multiply them, right? And can you explain like what are the functions? Are the function elements of the field or the vector space? Yeah, the functions are elements of the field. So the standard ones are the following. You can have function of complex. So namely you take complex to complex. And yeah, I mean, these are the two main ones. And right. So yeah, I mean, yeah, so we take the functions are over the field. Yeah, is that okay?
But so sorry, the functions are over the field, meaning the functions are in the vector space. I'm still a little confused. So like, what
So-
if the
The vector space is the space of functions. So V is functions of F over R. Like,
V is the functions, but then the field is either R or C, like whatever the.
yeah, whatever the field, the underlying field, but usually we just take them real and complex. Yeah.
Oh, okay. And it just has, it's like it's closed under addition and multiplication. And like
Yeah,
scalar
that's the
multi-
beautiful
oh.
thing, right? Like e to the x
Oh.
plus, I don't know, x squared is still a function over R to R.
Oh, and so it's still in the vector space, and that's why we say it's okay.
Yes,
Oh,
yes.
thank you. That was my question. Thank you.
Good question. Please ask it in class. Okay, thank you. Yes. Yeah, that's a very good question. Thank you. Okay. Anything else? Any other question?
So if there are no other questions, I had a
Yeah.
question about
Yeah, of
the like
course.
for the still for diagonalization because like I've forgotten math 223.
Right.
Is it okay if I ask like because I know it's not really related?
Yeah, no, it's
but,
fine. Yeah, go ahead.
So when we diagonalize, we say like a matrix, let's say M is diagonalizable if we can write it as a product of like, you know, P X
Right,
P
yeah.
power minus 1, right?
Mhm.
It's just that so I understand that P would normally be a vector where the columns
Yeah,
are the
you
eigenvectors
take
of M.
like a V11, V12, or no.
Yeah, exactly.
Yeah,
But
yeah.
how
So
do we
you
know
have,
which one is the first eigenvector? Like, let's say if I have 3 eigenvectors, one for each eigenvalue.
oh, it doesn't
how do I-
matter.
Oh, you can just switch the columns. It doesn't matter.
Yeah, they're all linearly independent.
Oh, so that, but then we would have to change P inverse accordingly, right? Like it
Yeah,
still has
yeah.
to
That's
be.
the thing, right? So that's why this is consistent because, yeah, exactly. That's why. Oh, I see what your question is. Like if you swap them around, yeah, the whatever you do there, it gets canceled out by P inverse.
I
That's
see.
why.
Okay.
Yeah, good question. Yeah.
And there's a more like elementary question, I guess. So like if we think of like M like normally represented in the like the normal B like E1 E2
Yeah,
basis,
you're
like
you're
1,
talking
0,
about
0, 1.
like T of E.
Yeah, so that notation that just means T acts only in E, right? Like it's like there's no
Yeah,
change of
I
basis.
know. Like
it's just
okay, you know what? I might as well just write this. Yeah.
okay, but when you write, for example, T from U to V, does that mean that the matrix T both performs a linear transformation and does a change of basis? Is that what that means?
Yes. But you know what? I talked to the other instructors, and I don't think we're gonna cover this. So.
Oh, okay. So I'll not. Yeah,
I
'cause that
wouldn't
was
worry,
very
but
confusing.
I thought it was interesting because it shows up in data analysis, and you know, like you don't always have the same basis for your transformations.
Yeah, it's just because I'd never seen that in like Math 223.
Yeah,
like,
yeah, I know,
online
but
and
it's applicable. Like it's a real thing. It's
oh,
not
of
like
course, yeah.
yeah.
So just one last question. Sorry, I know like it's like way
No, it's
past
fine. Go
time.
ahead. Yeah.
But also, if we think of like this as a change of basis, like M to D as a change of basis, like transformation, like, well, I guess my question is this: just the intuition behind, because if we think of like M as the product of the 3 matrices, you can think of like P based on what I understand. You can think of P inverse as first changing your basis from like the standard basis to the basis of the eigenvectors.
Right.
And then D doing some transformation in the eigenbasis, and then P taking you back from the eigenbasis to the standard basis, right?
Perfect. Exactly. So this guy
But
takes you. Yeah. No,
yeah,
exactly.
but I
You're
don't
right.
understand because like when we think about P, we say P like if I do the like element, like the identity matrix, products by P. Do I not change identity to P? Because like I'm
Wait,
confused as
can
to
you
why.
repeat the, sorry, what are you saying?
So it's just like I'm confused because if we do P times the identity matrix, so like P on the left, identity matrix on the right, is that not
Mhm.
is that not going from identity? Is that not going from like what is it called? Like from the standard basis to the P basis or like eigen basis?
Yeah, but then you come back.
No, I know. It's just that I don't understand why P basically takes you from eigen to standard and not from standard to eigen basis. That's what confuses me. Because in this structure, P inverse takes you from standard basis to eigen basis, right? And then you do
Well,
the.
I mean, I
transformation
wouldn't
and
quite. Okay, let me see. What are you saying? Why are you acting on the identity matrix?
because I'm just trying to understand why P goes again. So in the structure, like P inverse,
Like,
it's,
okay,
yeah.
just a second. So you have to act on V in the standard, like every vector, right, has two notations. Either you can write it as with respect to the basis E,
Mhm.
or you can write it with respect to the, let's call it the eigen. Okay.
Yeah. Yes.
And then here we're acting on VE. And right.
So to my understanding, P inverse times VE takes VE to V eigen, right?
Yeah, so this guy takes you to some guy in
Like V eigen.
in like a V eigen, and then you act with your guy, and then
And then like
you come
yeah.
back
So what
to
I don't
the,
understand is what. So basically,
guess
yeah.
it's
So
like
we have TV
this.
eigen after we do like D, we get like some transformed V in eigen. What I don't understand is why when we act on it with P, we go back to the original the standard basis. Because when I look at P, all I see is how you go from standard to eigen basis, not how you go from eigen basis to standard
No,
basis.
but you gotta be careful, right? This matrix P, this is not, these are the, like each of the vectors, right?
Yeah.
They are the eigenvectors, but written in E.
So it's just like the intuition, like I'm not like kind of getting
Well, I mean,
why.
well, that's why I wanted to talk about the, but I mean, this is the change of basis. I will go back and study a little bit of change of basis because this is exactly all that is. I think your question just comes down to why does the change of basis look like this?
Yeah, basically. Yeah.
And the answer was you take a vector I and you write it with aij of j. And are you there?
Yeah. So yeah,
Oh,
I'm
yeah.
listening. So
Yeah, and then right. So each of these entries are just these aij's, and so then what's the question? Oh yeah, the question is why does P act on?
like when we act by like when P acts on a vector, but in that formula, P acts on a vector that is in the eigenbasis, right?
Right.
So
Yeah.
whatever
This
P
is
acts
exactly.
on yeah, and it takes it to the standard basis. That's just the intuition. Because when I look at P, I see like the matrix that takes you from the standard to the eigen, not from the eigen to the standard.
Right. Okay. Let's see. So how do we do this? So this is eigen, but what is this eigen? This is just so we write AB, but this is really A of V1 plus what do I want to say? Yeah, A of V1 and B of V. Okay, just a second. So A of B eigen, that means that your vector is A V1 plus B V2, right?
Yeah, and V1, V2 are the eigenvectors, right?
Right. Now,
Yeah. So that's like the true vector form.
yeah, this is like in the standard form. So then, let's see, what do I want to do here? How should I go about this? Maybe I should replace this. Let's see. What do I want to show you? So let me see what your question Are you asking?
Like I'm asking, like because the way we like, if I look at the
Oh, okay.
eigenmatrix,
Here's
right?
like, I mean, just a second. So, this change of basis, right? So you write everything in terms of EJ, and then this guy will give you some CD in terms of the standard basis, right?
What?
What?
So what is A1? What is the matrix on the left right now? That's
So
you're
this is
saying
the
that's P,
change
right?
of basis.
Like that's P, right?
Yeah, that's the P guy, right?
Okay.
And I mean, I don't know, but you're basically asking why does the change of basis look like this? And so we have to like, let's see. So it's hard to do without an example. Okay, so let me see. So we have A11A and A12B
Yeah.
and A21A plus A22B. And then, okay, so then what do I want to say? So this guy is the coefficient for V1.
Yeah.
And this guy is coefficient for V2. So you can write this as A times V1 plus B times V2, okay?
Yes. Oh, like just in the column way. Oh, I see.
Yeah. So
And then that is the like the true
then
form of
that
the
is
vector.
an element of,
Oh, I see. Okay.
yeah.
Oh, okay.
So this-
okay. Thank you. It was just looking at it in the column way. Okay, I missed that. Yeah. Okay, that was my that.
Okay.
That makes sense now.
All right.
Thank you. Thank you for taking the time. I greatly appreciate it.
Yeah, yeah.
Have a great day.
Oh, yeah, you
No,
too.
no, that's all good.
Any questions? All right. See you on Friday, guys.